So in the previous sessions we have discussed the mathematical statement of the second law of thermodynamics in terms of the closure theorem applicable for reversible processes and inequality of closures applicable for irreversible process in general. And during the derivation of the closure theorem and the proof, we could obtain a new thermodynamic quantity we have introduced, which was named as entropy, and we have obtained a relationship for the change in entropy during a reversible process. The equation that we have used is ds is equal to d bar q reversible by t. So ds equal to d bar q reversible by t. This equation is the change in entropy. It gives the change in entropy of the system when an infinitesimal amount of heat d bar qr is absorbed by the system. Okay, so ds denotes the infinitesimal change in the entropy of the system due to the absorption of an infinitesimal amount of heat under reversible conditions by the system. So that is ds, right? And here if you analyze this equation, you can see on the left side you have got an an exact differential. We have seen that entropy is a state function and hence it is represented by an exact differential, whereas on the numerator of the right side you can see d bar qr, which is an inexact differential. And we have mentioned the role of this 1 by t. The role of this 1 by t in the equation is that of an integrating factor. Means by introducing 1 by t in the expression, this d bar q r by t as a whole becomes integrable. And that is one method to find out the change in entropy during reversible process. So what we'll be doing in this session, we'll be finding out the change in entropy of our ideal system, which is nothing but the ideal gas, under various conditions. Means we will try to obtain the entropy change of the ideal gas system in terms of different thermodynamic coordinates. That is, we will be obtaining an expression for the entropy change in terms of the volume and temperature of the system. Means we will get rid of the pressure from the equation. In another case, we will be obtaining the equation for entropy change in terms of the pressure and temperature of the system, means which is devoid of the volume. And the third case, we will be obtaining entropy change for the ideal gas system in terms of the pressure and volume, means that equation will be devoid of temperature, right? So one thing to be kept in mind is that the equation number 1, what I have written here, this equation represents the infinitesimal change in the entropy corresponding to an infinitesimal addition of or transfer of heat d bar q. So see, whenever a system is going from an initial thermodynamic state to a finite thermodynamic state following a reversible path, there will be a large amount of heat that is getting added up. Okay, and it may so happen that with every bit of or with every small quantity of heat that is added to the system, the temperature of the system may be going on changing. Okay, so initially say that the temperature is T1 or Ti, and you supply an amount of heat d bar q to the d bar q1 to the system. So what will happen is that maybe the temperature of the system will be getting increased by a bit. Slowly, infinitesimally it has increased. Okay. Now you can calculate due to the addition of that d bar qr how much entropy has increased by simply taking d bar qr divided by ti. But now in the next case, now the temperature would also have increased. You can see that due to the addition of heat, the temperature may increase depending on the condition. So when you add the next increment, when you are giving the next lot of heat, okay, d bar q r 2, if you give it, what will happen is that the temperature in the denominator in the previous case is not the same in the present case, because the temperature also would have increased. So there are cases where due to the addition of heat, even though infinitesimally, okay, bit by bit, what will happen is that the temperature of the system is also going on increasing. So in that case, if you have to find out the total change in the entropy at the end of a process going from initial to the final, means from pi, vi, ti to some pf, vf, tf, you cannot treat this temperature in equation number 1 in the denominator to be a constant. So in that case, the temperature is also a variable. Okay, so that is one thing to be taken care of. So ds is equal to d bar q r by t when you are using, okay, for a finite process. This is for infinitesimal change, but for a finite process, this t in the denominator will be variable, and you will have to perform what is known as an integration to obtain the total change in the entropy. So that is to be taken care of. So, but in some special cases, for example, during phase change, okay, so for example, some phase change and all, what you can do is that, you know, during phase change, like melting or evaporation, all those things, you know, the temperature of the system will be remaining constant. So in that case, what you have to take care is only the amount of heat added. So T is a constant. That's a very special case. So if this is one thing that you take care of in problems, if T is equal to a constant, example, the best example is phase change. So you'll be dealing with a large number of phase change problems. Okay, so phase change. So there you have got a convenience. What you can do, you can find out change in entropy. So during phase change, there will be a change in it to be accompanied by a change in entropy. So I can call it as some delta S. So that is a finite change in entropy, delta S. So you can directly treat this delta S is equal to Q upon T. So I'm not going after ds and all. There is no need of any increment, or there is no need of any infinitesimal thing, because you are not going to integrate it, because the temperature is remaining a constant in this particular case. So delta S is equal to simply Q by T. And what you can do for this Q, okay, so Q can be just substituted in terms of latent heat. Okay, so you know that the latent heat we have defined as something like Q by EM, right? Is right? So Q by EM, that is latent heat, whether it is latent heat of vaporization or latent heat of fusion, or depending on the situation. So therefore, what can you substitute that Q is equal to simply ml? So Q is equal to M mass, okay, mass of the liquid or mass of the sample, into L. L is the latent heat divided by T. So in most of the problems of phase change, you can directly calculate the change in entropy by using the simple expression. The reason is, remember, because in those cases the temperature is remaining a constant. But in general, if the process involves a continuous change in the temperature due to the incremental addition of heat to the system or removal of heat from the system, you are supposed to use the expression number 1 that I have written, and so you will have to just perform integration okay, on both sides within proper limits after converting this numerator d bar q r in terms of the thermodynamic variable. So what I want to conclude is this one. In different cases, you can calculate the entropy change by using equation number 1 by substituting for d bar q r using the first law of thermodynamics, the differential form of the first law of thermodynamics in proper terms. So in this session, I'll be discussing 3 different cases. As I told you, see entropy change in terms of V and T, in terms of P and T, and also P and V. Maybe I will depend on 2 different videos for this one. So anyway, let's begin with the expression for entropy change in terms of volume and the temperature of the system in going from an initial state to the final state. Okay, so what we assume here is that the system that we are discussing here, okay, the thermodynamic system that we are discussing here, it was initially having say like, you know, so you can just imagine some okay, thermodynamic coordinate axis and role, so whatever it is, so it can be some PVT, okay, whatever it is. Okay, so you can just think of a three-dimensional thing, and the system was initially having a thermodynamic state, say this one, so this is I, so you can imagine that its coordinates are some Pi, okay, Vi or P1 V1 T1. Okay, so let me take it like that, it's easy to write P1 V1 and T1, and this is initial state 1. And suppose that the system, okay, just changes reversibly. I'm considering the reversible case only here because that is easy to deal with now. Okay, so suppose the system is just changing, undergoing a process reversibly, and finally it is setting to a second state, thermodynamic state, which is denoted by the parameters P2, V2 and T2. This is the case. Okay, and in this derivation, and our system is what? The ideal gas system. Our system is ideal gas. So it's a very special case. Okay, and you know that the entropy of the system by definition is a state function, means the system will be having a definite value of entropy at state 1. So let me call the entropy of the system at state 1 be S1, and the entropy of the system at state 2 be what? S2. Okay, but unfortunately you know that the thermodynamics do not give you absolute values of this entropy at any point. S1 and S2 you are not bound to calculate. You won't be able to calculate by the laws of thermodynamics, okay, directly. Okay, instead what thermodynamics laws permits you to calculate? Only the difference in entropy. Okay, doesn't matter, that is enough for us for the time being. So what we will be doing in all the three cases that I have mentioned here is that we will be calculating the change in entropy. Okay, I can say change in entropy is what? The entropy final, that is S2 minus S1 in all these three different ways. S2 minus S1, that is our change in entropy, okay, of the ideal gas system in going from state 1 to state 2 along a reversible path R. And for that we'll be using equation number 1 with the proper integration. So on integrating this ds, you can see that on integrating ds from say that S1 to S2, the endpoints, you will be able to get what? S2 minus S1. Okay, and for that you will have to perform the integration on the right side also over proper limits by just making some suitable changes, substitution for d bar qr, because d bar qr is not an exact differential, so you cannot directly integrate an inexact differential, so you'll have to just convert it. So let's see how to do that in the next slide. Okay, fine. So we'll start with entropy change of the ideal gas system in terms of volume and temperature. Right. So here we are. So our aim is to calculate the entropy change in terms of the volume and temperature for an ideal gas system. So it's a very, very special case. Be careful about it. Okay. So as I told you, our equation of use will be equation number 1, what I have written there, the basic definition of infinitesimal change in entropy ds. So keeping that equation in mind, let me begin. Okay, so let me start with that one. See, we have right the first law of thermodynamics, or yeah, I can start from there straight away. So we have the first law of thermodynamics. You know the first law of thermodynamics, we can write it in the differential form, right? In differential form. You can skip many of the steps that I am writing here by recalling what we have done in maybe module number 2 and all. Okay, first law of thermodynamics in differential form. Okay, what is that equation? That is d bar q. I'm just doing it for a reversible process here, so I'm putting the subscript r here, is equal to du plus pdv. du plus pdv. Okay, so these are some equations that I won't be using, but only for an introductory remark I am just writing all these equations. You know how this equation comes and all, I need not tell you, you can refer back. Okay, so if you want I can just remind you this one. Only in this particular video we'll be doing that. Okay, we had the first law of thermodynamics. Usually we used to write some du is equal to, okay, d bar q plus what, d bar w. This is the way in which we have just written it. Okay, so on one side you have got a exact differential, on the other side you have got the sum of two inexact differentials, and I can substitute, I can again write this one as some d bar q is retained as such because we need the heat. Okay, d bar q, and you know for a hydrostatic system d bar w can be expressed as minus pdv, so minus pdv, right? Okay, now you know I need this d bar q, so I retain it there, and minus pdv is taken to the other side, so you get this particular equation du plus pdv. That's the way in which you can begin depending on your memory. You can either begin from this particular equation what I have written here, or you can start, okay, directly from here. So it all depends. Okay, so you can even begin from another equation that I am going to tell you. See, you know, I don't know whether you remember during our derivation of Mayer's relationship, relation between Cp and Cv, hope you remember that. Okay, or to prove that Pv raised to gamma equal to a constant, we had started in the same way here. Okay, and we concluded the equation for d bar q in another way. So I'm straight away writing and okay, using okay, what you can say that PV equal to nRT. So we use this equation, so you can just check it back with your notes. PV equal to nRT for ideal gas system, because we are talking about ideal gas system, and the definition of CV. Okay, and the definition of CV for an ideal gas. So we proved that CV for an ideal gas is equal to du by dt. Okay, so du by, or dou u by dou t at constant v, du by dt, that is enough. Okay, so using these expressions we could prove that, okay, d bar qr that is equal to, okay, instead of du, how do you write it? Can you write as cv dt? So cv dt, when I write this equation it will be okay, reminded. So cv dt, I can write this one as cv dt plus simply pdv, cv dt plus pdv. Okay, so that is the expression. So in my opinion, if you can recall this equation, this is also another form of first law of thermodynamics in differential form, written in terms of the CV. Okay, so let me start from here. That is what I begin with. So you can get rid of all these okay, these steps when you do it in your notes and all, and you can always refer back. We have the differential form of the first law of thermodynamics in terms of CV given us d bar q r is equal to cv dt plus pdv. That's my equation number 1 to begin with. Now, since we are talking about an ideal gas, can't I substitute for P? In this equation there is P coming, but what is our aim here? We have to obtain an equation for entropy change in terms of V and T. So basically remember what is our strategy. Okay, so we have to write the final expression for entropy change in terms of volume and temperature of the system. Means I should be able to get rid of pressure. Okay, so but in my equation number 1 there is pressure. So what I have to do? I have to substitute for pressure in terms of the volume and temperature of the system. So that can be done from this equation, PV equal to nRT for ideal gas. So equal to, directly you can write this. So what will that be equal to? It will be equal to CV dt. It's quite simple and straightforward derivation. So what is P equal to? P can be written as nRT by V, right? nRT by V. So I'll be writing it as nRT. So this is a plus here. nRT by V, that is understood, dV. Okay, so that is my equation now here. So let me say that this is my second equation. Okay, so you have got d bar qr. Now you know what is our strategy in finding entropy change. I already have mentioned you, we will be using our equation for change in entropy. Is there an infinitesimal change in entropy? We have Okay, whenever we bring in a new equation, let's start with some connectors like we have or we know. Okay, all this. Okay, so only just a connector. We have what is this one? ds. We have what is ds? What is ds is equal to d bar qr. ds is equal to d bar qr upon t. Is it not? So let me say that this is my third equation. So this is our motivation, right? You have got d bar qr here, and ds can be calculated by just d bar qr by t. So can you substitute okay d bar qr from equation number 2? What will be that? So it will be equal to, I can write, so this is equal to cv dt just by t. Okay, so actually I am multiplying by 1 by t throughout equation number 2, because 1 by t, as I told you, is that is our integrating factor. Okay, so it's a mathematical technique actually what we are performing, plus what we will do is that nr. Okay, so when you divide by t here, so that 2t will be getting cancelled. So what remains is here nr. Then let me rewrite it like this: dv by v, and the t and t has got cancelled, right? Is it not? So that is nr dv by v. So that is my equation number 4, right? Okay, now you know what to do. Our aim is to get the entropy change in going from state 1 to state 2, or initial state to final state. So as I mentioned in the previous slide, initial state 1 is characterized by the values p1, v1, t1, and say s1. S1 is also thermodynamic state function. Okay, and the state 2 of the system is characterized by p2, v2, t2, and s2, right? Okay, so and our aim is to get the difference between s2 and s1. For that you have to integrate on both sides. So integrating both sides. So on left side, my integration will be integral over the initial and final values of ds. So what is that? s1 to s2, s1 to s2, s1 to s2, right? So over ds, that is equal to cv times, you have to integrate our proper limits, cv times. See, remember one thing, we have seen that cv for ordinary temperatures, they are considered to be constant. Actually cv has got a weak dependence on temperature. We neglect that dependence here for ordinary temperatures. Okay, cv times integral from where to where? The temperature, let's say that it is from t1 to t2. Okay, dt by t, okay, plus next thing is what? nr integral from so here the integration is done with respect to v, dv is there, so you have to substitute the limits of v, volume 1, v1 to v2, v1 to v2, dv by v. Okay, that is the thing. And you know what will be the fate of this equation. So on integrating left side, you will be getting s2 minus s1 directly. Can you write s2 minus s1 directly? Okay, so I'm directly write this one, s2 minus s1, or delta s you can call it as, right? It's a finite change, delta s, because we have performed the integration, so it has become finite change, s2 minus s1 or delta s. So what is delta s is equal to, on the right side, let's say what happens. See, cv into, what will happen here? 1 by t dt. 1 by t dt is log, natural logarithm of t. Okay, so if you want directly write it, so log is not, you can skip one of the equation, or I can write it for example, log t. Okay, sorry, what is there under thing? cv is there, no? So cv into, this is capital cv, remember, cv into log t. Okay, from the limits t1 to t2, of course you can just rewrite that one. Then plus nr, similarly the next one is what? Log nr times log v in the limits what? v1 to v2. And once you substitute the limits, what will be getting? So I'll be getting s2 minus s1 is equal to, once again it is cv. Okay, you can just write log T2 minus log T1. So that is nothing but Cv log T2 by T1, right? Final temperature by initial temperature. Okay. So log T2 minus T1 plus what? Nr log, can you write V2 by V1. So that can be our final expression. So that is our delta S. Delta S is S2 minus S final minus S initial. So my delta S is equal to Cv log T2 by T1 plus Nr log V2 by V1. If you want, what you can do is that this Nr can be, you can express the final equation in different forms. If you want, you can write Nr as some by Mayer's relationship and or the previous equation, Cp minus Cv equal to Nr, right? Okay, capital Nr, that is capital Cp minus capital Cv is equal to N into capital R, right? So the same equation can be written as Cv log T2 by T1 plus Cp minus Cv in bracket times log V2 by V1 also. So I'm writing it here for the time being. So let me just draw it here. Okay, yeah. So or delta S is equal to, so let's use it in different forms depending on you can recall at least some of the equations. So Cv log T2 by T1, okay, plus I'm opening a bracket Cp minus Cv, so that there is some sort of a uniformity. Here there's a Cv, there is a Cp minus Cv, it will have some log, nothing else other than that. Okay, V2 by V1. Which equation is to be used depending on which variables are known to you. Okay, so depending on that you will be using that. So this is another equation that you can use. So this is also an acceptable final expression in terms of, you can see that here what all only things comes, Cv comes, Nr comes, temperature T and V are coming, temperature and volume are coming. So that is in terms of the volume and temperature. So if instead of total specific heat, if you are given with the molar specific heat, okay, molar specific heat, then also you can just write this one. See, you know what is molar specific heat? You know that the small Cv is equal to capital Cv per mole. Okay, per per En I had right, per number of moles if it is molar specific heat. So I can write capital Cv, whenever I see capital Cv I can write as what? N into small Cv. That can be done. Similarly this Cp minus Cv also you can just write as what? Okay, in the same manner or whatever it is. So if you write it like this, this equation, let me call by some name, this is equation number 5, and let me say that this is equation number 6. You can make changes by using this relationship. Wherever you find Cv, you can write N into Cv. Okay, and wherever you find Cp, capital Cp, you can write as what? N into small Cp, and you can rewrite that equation. So these expressions, okay, what we have found out, equation number 5 or 6 can be used to calculate the entropy change of an ideal gas system undergoing a transformation, okay, in terms of the volume and temperature. So that's it, and in the next video we'll be same manner we'll be deriving expression for the entropy change in terms of other two variables as well. Okay, thank you.